Hi, and welcome back to Geology. I'm Miss Sparks, and today we're talking about absolute age of rocks. And so previously we've already talked about the relative age of rocks. And so we're breaking our unit into three different sections: relative age, absolute age, and then kind of going into the different periods and eras and geologic time of the Earth. And so this next couple of days, we're going to spend time breaking down how scientists and how geologists can look at the Earth and figure out a more direct age of a rock layer or a fossil, in order to kind of give it a much more an exact date or time period, versus just saying what we did with relative age, is that older layers of rocks are on the bottom, younger layers of rocks are on the top, and we can identify them just by how those rock layers have fallen, and then along with different types of erosional process. And remember, we talked about those three types of erosional processes with our relative age, which is angular conformities, disconformities, and our layers of cross-cutting. And so we were able to take those and kind of figure out just how old some of the rock layers were by just looking at a cross-section or a picture of it. Absolute age is going to be a little bit more direct. There is a little math that's going to go with it. And we are going to talk about radioactive decay and how we can find the half-life of an element in order for us to figure out exactly how old a rock layer is. And so please get out a sheet of paper and pencil and make sure you take some notes today. So the first thing is that absolute age just is an actual age. Like you have an age on your date of birth, you then turn a year older. This is kind of the same idea when we are talking about absolute ages. We're able to find a good, not a perfect, not like saying the rock was formed on July 1st, 1972, but we are looking at a more general, a more specific era that we could say this rock was formed 4.5 billion years ago, or this rock is 3,000 years old, or this fossil is yada yada. And so absolute age is something way more direct. So scientists often need to know the actual age of the rock layers in order to tell more about it, meaning what kind of environment did it live in? What is the creatures and organisms that might have lived alongside of it? What type of weather did this organism live through? Or what type of weather did this rock form in? So we want to know more about it than just that the layer below it and the layer above it are younger and older. We want to know much more specifics, and that's what absolute age is going to allow us to do. It's allowing us to find the actual age. And so there's 5 different ways in which we can use to help identify absolute age, and that is the rate of erosion, the rate of deposition, varve counting, radioactive decay, and carbon dating. And these last 2 are going to be the ones we're going to spend the most time kind of talking about and moving through and learning how these can be very, very, very helpful for geologists and scientists to answer absolute age questions. So the first one is rate of erosion, though. And this is actually really, really important because we can find out a lot of information just by how rocks erode down. And so I have a picture here of Niagara Falls. And Niagara Falls is a great example of a erosional process. Is that this is a very, very large river that is running through an area where it has eroded down this cliff type area. Over time, though, there's tons and tons of water that is going over Niagara Falls, and at some point it is going to erode far enough back that it might just become a river again. Grand Canyon is another great example of a rate of erosional process. So what the actual definition of it is scientists measure the rate at which a stream erodes its bed, meaning just the canal or the channel that it runs through. And it can measure the age of that stream. So we're able to kind of look at how much water is moving through that system and how much sediment is it taking along with it. So once again, Niagara Falls, great example. It's that it's curling, eroding off. This right here is actually a very sturdy granite cliff. And so it's really, really strong. Remember, we talked about granite being igneous rock. It's compacted. It formed intrusively at a very slow rate. And so those cavities or those elements and those minerals are able to bond together. And so this granite here has that process. The Grand Canyon is not a good example of erosional because of the sediments that are there and how easily they can be eroded away, and then they're deposited way far out. So we can't actually measure it as nicely as we can with Niagara Falls. The rate of deposition is almost like the opposite or the second part of the rate of erosion. So deposition, we've heard this term again, if you think back to sedimentary, it's just the idea that things are being deposited. Kind of see it in there, deposition. So this helps determine the age due to the amount of sediments deposited in an area. So somewhere the Grand Canyon eroded a whole bunch of materials away, and then it was deposited somewhere else, probably more than likely somewhere in the Pacific Ocean. So in general, about 30 centimeters of sedimentary rock deposit equals about 1,000 years. So we're able to use that. Kentucky is a great example of figuring out the rate of deposition. We can look at the thickness of the layers and normally figure out, was this a rainy season? Was this a season where there was a whole bunch of ice? Was it a dry season? Just by the thickness of what we're looking at. Because normally, once again, Kentucky is a area that once was a shallow seabed, and so we can use that to our advantage. This is not always the most accurate because once again, you are sometimes taking in an element of guessing, like, okay, well, we think that 30 centimeters might equal this, but maybe there was a years of rain and rain and rain or wind, and that could have caused something to change just ever so slightly. And since we weren't observers at that time, sometimes the rate of deposition is not always the best of ways to go. Varb counting is our third way in which we can absolute age rocks, and this is due to the particles of, once again, layering. So let me read you this. So some sediment rocks show a diphite annual layer. These layers are called varbs. They consist of light colored bands of coarse particles and dark bands of fine particles. Think of this as a tree ring, is that you can cut open a tree and look at the rings to figure out the growth cycle of this tree. This is kind of that same idea, but once again with rock layers, is that there's going to be some years where it might have a lot more particles that are deposited and some are not. We can use this with sediment. We can also use varb counting with ice. We can figure out how much area was maybe chilled for a much longer period of time with more carbon in it than not carbon in it. So there's different ways we can kind of look at that. The two that we're going to spend the most time talking about, though, is radioactive dating and carbon-14 dating. And so we're going to spend some time kind of talking about these two, and then we're really going to break it down. And so radioactive decay is the idea that we are looking at an element in which over a period of time, it becomes unstable and it releases neutrons. So protons and electrons are really important because those are kind of like the elements DNA. If we take away a proton or electron, that completely changes the element. But radioactive decay allows for that neutron to be released out of the nucleus, and then we can see a different type of weight or mass, an AMU, if you've taken chemistry. That's going to allow us to figure out what's actually happening with that element. So radioactive isotopes have nuclei our nucleus our neutron that emit particles and energy at a constant rate. So let's say that we're looking at uranium, and it has, let's say, a radioactive half-life of every 10,000 years. So every 10,000 years it's going to spit out another neutron. It's releasing it at a constant rate over and over and over again. And we can use that as like a time machine and work backwards to figure out how old an object is. So as an atom emits particles and energy, it changes into a different isotope, meaning that its mass changes. And so the rocks contain radioactive isotopes because rocks are made out of minerals and minerals are made out of elements. So radioactive decay is a really easy way for us to figure out how old certain rock layers and certain rocks are. Radioactive isotopes function as a natural clock because we can figure out the amount of time that it's going to release something and kind of go from that over and over again. And so next we're going to talk about the half-life. So once again, hopefully this was helpful, our different ways in which we are looking at absolute age.